Welcome back. In this video, we're going to continue learning about valence bond theory. Specifically, we're going to use VSEPR and Lewis structures in order to determine what hybrid orbitals are involved in covalent bonding. We're going to go more in depth about sigma versus pi bonds, learning how to differentiate between them, indicating which orbitals are used to make those bonds, as well as talk about how multiple bonds are formed and why there is restricted rotation around those multiple bonds. Let's begin. So let's review what we learned already about determining hybridization. Based on the steric number for a given element, we can determine its hybridization. Or in other words, the orbitals that are used in order to make covalent bonds. If an element has a steric number of 2, then it requires 2 electron domains that are identical. To do that, it takes and hybridizes 2 orbitals, those being the s and the p orbital, to make 2 orbitals which are sp hybrids. If you have 3 electron domains, if we need 3 total electron domains, then we need 3 identical hybrid orbitals. That is made up of 3 atomic orbitals, 1 s and 2 p's, giving us 3 orbitals which are all sp2. For a steric number of 4, we have 4 total orbitals that are needed. And so we use all the p orbitals and the s orbital. That makes 4 identical orbitals which are sp3 hybridized. Now, in the case of the sp hybridization and the sp2 hybridization, there are leftover p orbitals. So what happens to those leftover p orbitals? We're going to learn how they are used. So a double bond consists of both a sigma bond and a pi bond. And this is where those leftover p orbitals are used. They form the pi bond. So if we look at the molecule ethylene, each carbon atom in ethylene has 3 sp2 hybrid orbitals and 1 leftover p orbital that has not been hybridized. We could imagine it looking like this diagram here on the left. We have the sp2 hybrid orbitals, which are used to make the bonds between the carbon and each of the 2 hydrogens, and we're left over with the unhybridized p orbitals. Each of the sp2 hybrids overlaps with an s orbital to form the ch sigma bond, and then 2 sp2 hybrid orbitals, 1 from each carbon, will overlap to form the sigma bond in the carbon-carbon double bond. Also, we have overlap of the atomic p orbitals from each carbon, and that forms the pi bond. And this is the second bond that's involved in the double bond. So if we wanted to count up for this molecule how many sigma and pi bonds there are, we would identify each sigma bond as being a bond that involves either an atomic or hybrid orbital that goes in between the nuclei. So here we have 1, 2, 3, 4, 5. So there are 5 sigma bonds, and then there is 1 pi bond between the carbon atoms. Because the pi bond involves the space up above and below the atoms, this restricts the ability of that bond to rotate along its axis. Normally, with a sigma bond, the molecule is free to rotate. However, because we need to have an alignment of the tops of the p orbitals and the bottoms of the p orbitals in order to form the pi bond, this prohibits the rotation of that molecule around that axis. So we see that this does not happen. We do not have rotation around the carbon-carbon bond. That would break the pi bond. Now, we can break those bonds, but it requires energy. So this is what happens when light hits vitamin A. Vitamin A is a vitamin that is essential to human diet, and part of why it's essential is because we cannot produce it. Vitamin A can be converted into beta carotene, which is used in our eyesight. And when light hits vitamin A, what it does is it breaks one of the double bonds, which allows the molecule to then rotate. That double bond then reforms, and then it gets stuck in this position until light hits it again. And as this process occurs, when light enters our eyes, our brain can interpret those electrical signals and the shifting of those molecular bonds as light, as what we see. Let's now talk about a triple bond. A triple bond consists of a sigma bond and two sets of pi bonds. So we only get triple bonds when we have molecules that have two electron domains. Therefore, they are sp hybridized, and that leaves two sets of p orbitals that are left over. Each set of p orbitals will interact with the paired p orbital on the adjacent atom. As those overlap, those form a pi bond. So we would have a pi bond that exists up above and below the carbon atoms in this case, and then on either side of the carbon atoms. So a triple bond consists of one sigma and two pi bonds. And so we can understand the nature of multiple bonds by taking a look at cases where they don't occur. Carbon, for example, forms double bonds and triple bonds. However, silicon does not. Now, why not? Well, in order to form a double bond or a triple bond, remember, we need to have overlap of the unhybridized p orbitals. And because those orbitals are not overlapping head-on, but side to side, you need to be close enough, the atoms need to be close enough for those orbitals to overlap. The silicon atom is much larger than the carbon atom because it's in the period beneath it. Because of the increased size of the silicon atom, the silicon-silicon sigma bond is longer than the carbon-carbon sigma bond, which means that there is a larger distance between the p orbitals of the silicon atoms in this theoretical scenario. Therefore, there is weaker or almost no overlap between the p orbitals that could exist with a silicon-silicon double bond. Therefore, this does not exist. There's simply too much space and there's not enough overlap between the atoms. Let's now do a practice problem. I'd like you to pause the video and try this on your own, then come back and I'll walk you through it. Welcome back. So we want to know what orbitals are used to make the hydrogen-nitrogen, carbon-carbon single, and carbon-oxygen double bonds that are shown in the molecule that you see on your screen. So the first thing to do is to remember that each point represents a carbon atom. Okay, each of those represent carbon atoms. These are indicating that we have reached the end and we're attached to whatever other atom is there. So we have nitrogen, oxygen, and oxygen that are attached on those ends. But these points here represent carbon atoms. Also, there are hydrogen atoms attached to the carbon atoms to complete the octet. So in the case of this carbon atom, it only has two bonds, so we need two more bonds to form a complete octet. And the reason we need to identify which elements are bound to which others is because we need to determine the hybridization. Now that we know how many electron domains there are for each atom, we can determine the hybridization involved. So for nitrogen, it's sp3 because there are 4 domains. Remember that lone pairs count as a single domain. Carbon has 4 bonds, so it has 4 domains and is sp3 hybridized. This carbon has 3 domains. It has 1 for each of those bonds and then 1 for the double bond. Even though the double bond is larger, it only counts as 1 electron domain. Because it's sp2 hybridized, we do need to account for the leftover p orbitals. This oxygen is sp2 hybridized as well. It has 2 for the electron domains and then the unhybridized p orbital that are left over. Finally, we need to recognize that the hydrogen atoms are not actually hybridized. They only have the 1 valence electron, so they don't need to go through the hybridization process in order to form the bond. So all we need to do now to determine which combinations are involved to make the bonds is to literally combine the notations for the hybridization. So the bonds are made by combining the atomic and or hybrid orbitals together. So the hydrogen-nitrogen bond is made by combining the hybrid and the atomic orbital. It's an S with an sp3. The carbon-carbon bond is made by combining the sp3 orbital of the carbon in the middle with the sp2 orbital of the carbon on the right. And then the carbon-oxygen double bond, it is made up of, the sigma bond is made up of the sp2-sp2 overlap, and the pi bond is made up of the p to p overlap. Okay, let's try one more problem now. Now that we've looked at that molecule, determine how many sigma and pi bonds are in that molecule. Pause the video and try this on your own. Welcome back. So we've already looked at the structure. We need to remember that a sigma bond is made by the headlong overlap of the orbitals, whether they're atomic or hybrid, and that's characterized by a single bond. Pi bonds exist when we have double bonds. Remember, a double bond consists of a sigma bond and a pi bond. The sigma bond will be in between the 2 atoms, and then the pi bond would be from the overlapping orbitals on the sides, on either above or below those atoms. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8 sigma bonds. Oh, I've miscounted. 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds, and 1 pi bond. So the answer is D. Thanks for watching this video. Have a great day.